Okay. Welcome, young astronomers. I hope you all had a great weekend. We are finally done with our toolkit. We've learned the laws of the universe. We've learned all of the information we can get from studying gravity and studying the light from objects. And now, for the rest, not the entire remainder of the course, for much of the remainder of the course, we're just going to study all of the objects in the universe. And then at the end, we'll talk about how the universe itself was born. But we're going to start with stars and planets. We'll specifically start with the solar system. For the longest time, that's all we knew about. We actually came up with a model of how the solar system worked, called the Nebular theory, how the solar system came into being. And we've talked about it. Hopefully you've started reading about it or watched the videos. It was a collapse of a giant cloud of dust and gas that turned into the sun and the planets. That's what we're going to learn about this week. Before I do that, are there any questions or comments from anybody? All good? All righty, okay. Let's get on with the show then. We are in chapter 6 of our textbook. We're going to learn, as I said, about how the solar system formed. In order to really understand how the solar system formed, we'll use data from the other star systems. Remember our cosmological principle, that the laws of physics are the same everywhere in the universe. It is it may not be true. It's true to everything that we have measured so far. Right, as I said, all science is conditional, but it's gotten to the part that we've actually called it a principle. So it's fairly long in its study. Thousands and thousands of measurements have proven it to be true. To be honest with you, I just read a paper that maybe the laws of electricity and magnetism are different in different parts of the universe. It's probably due to the different ages of those regions, not actually them being spread apart, but it needs verification. It's one group of scientists, and actually there's another group of scientists who say that's not true. So there's a disagreement going on there. But no disagreements. I'm actually going to show you baby solar systems being born, baby star systems. Solar system, when we talk about a solar system, we really mean our sun. Sol is Latin for our sun. Now, even I will sometimes I'll say other solar systems, but I really mean other star systems. You might even read other solar systems. Let's talk about the solar system first. If we're going to develop a model on how this formed, we need to know the key features of the solar system. We briefly went over this the first week of class, but now we'll go over it again in a little bit more detail. And then we have 2 weeks where we will specifically talk about the inner planets, and then another week where we'll talk about the outer part of the solar system, including the planets and the dwarf planets and the asteroids and the comets. So again, this is this slide is very misleading. The only thing that's correct about this slide is the relative sizes of these objects. Just to give you an idea, that the planets are all much smaller than the sun. I can't put the whole sun on here. You can kind of use your mind to extrapolate this. Or you can see that the Earth here is about the size of a sunspot. So the distance between these objects is not correct. Also, they're never lined up like this. They're all in their orbits, in different places in their orbits. The only thing that's sort of lined up right now, by the way, and Mars is visible at night now, is Earth and Mars are about in the same, they're kind of lined up. It's the closest we're going to be to Mars in about 23 years. This is why we sent, it wasn't just the United States, it was launched before the class started, but several space agencies have sent new probes to Mars because it's at its closest distance right now.
Excuse me, Professor?
Yes.
I don't think that you don't have your screen shared, so you can't see your PowerPoints. Sorry.
Thank you. Well, that's good. You guys caught me but one slide. I appreciate that. Thank you very much. You are right. I'm not sharing my slide. You've seen this slide before, though. Hold on. Okay. Can you see the solar system now?
Yes.
Thank you very much. Okay, as I said, the distances aren't correct between these objects. The alignment is not correct between these objects. What is correct about these objects they are actual photographs, just kind of superimposed onto this slide. Every one of those is an actual photograph. The relative sizes are correct. You can see, first of all, you do need to know the names of all the planets. You need to know the order of all the planets. You have to have a relative idea of their sizes and mass. I don't expect you to memorize the mass of the Earth, but you do need to know that they're kind of grouped. They're kind of segregated. The 8 planets, anyway. We have inner planets, which are called the terrestrial planets, that are about the same size as Earth. Mercury's quite a bit smaller. Mars is a little bit smaller. Venus is almost exactly the same size and mass as Earth. But they are tinier and less massive than what we call the giant planets. And even the giant planets are kind of segregated. We have what's called the gas giants, which are Jupiter and Saturn, which are mostly made out of hydrogen and helium. It's not really in the gaseous state, so calling them gas giants is kind of misleading. It's more like liquid hydrogen and liquid helium, and even weirder states of hydrogen and helium. But on Earth, hydrogen and helium is mostly a gas, so that's why we call them gas giants. And then we have the ice giants, Uranus and Neptune, which are they're made out of mostly ice, not just water ice, but methane ice and ammonia ice. So we have the structure to the solar system that we're going to make a model on how this was formed. That has to agree with what we see here. Again, we also have dwarf planets. We also have an asteroid belt that's not pictured here in between Mars and Jupiter. And we have a Kuiper belt and an Oort cloud where the comets in the outer part of the solar systems reside. And amongst that Kuiper belt is where Pluto lives and some other dwarf planets. There's actually one dwarf planet that lives in the asteroid belt, which is called Ceres. These are close-ups of the terrestrial planets, or terrestrial worlds is probably a better name for it, because I include the moon in here. We're going to learn that the moon has more in common with the rest of these objects than it doesn't. And in fact, there's an intimate relationship between the moon and the Earth. Notice that you can see these worlds on their interior are very, very, very much the same. But you can see that their exteriors are much different and their atmospheres are much different. And we have to take that into consideration. Mercury has no atmosphere. The moon has no atmosphere. You can see they look very much alike. About the same size. Size is part of the reason why they don't have atmospheres. Part of the reason why their surfaces, they don't have any water, they don't have very many mountains, they have lots of what we call impact craters. And this dark area, as we learned earlier, it's not oceans in black and white, that's solidified lava. That is what the surface of the moon and Mercury is. It's actually much darker than this is with a brilliant sunlight bouncing off of it. They both have very, very dark surfaces. But you can see the Earth has water, has land. Venus has an atmosphere so thick that you can't even see through it. And Mars is kind of in between the Earth and Venus. So even though they're very much the same on the inside, they're what's called rocky planets. That's what terrestrial means, is they're rocky planets. They're very different on their surface and their atmospheres. And that has to go into our model, and we'll learn more about those differences as we go along. And then here's just some more images of the outer planets. Jupiter and Saturn, and Uranus and Neptune. And so those are just the planets of the outer system. Recall that that segregation, part of that has to do with the distance. The rocky planets are much closer to the sun. And then we have the gas giants that are 5 times further out than the Earth, 9 times further out. For Jupiter and Saturn, and then we have Uranus and Neptune that are 19 and 30 times further out. Our definition, kind of our ruler for the solar system is in AUs, right? That average distance that we put into Kepler's laws. That's 1 AU is the average distance between the sun and the Earth. It's 93 million miles. And again, this is the only thing I can really show you to scale in the solar system is this. If we were, we would build a model of this if we were live, if we were weren't remote, and we'd have to go out in the parking lot or out in the field to build it. Just to get the Earth to be the size of a tiny little pea, we have to build a giant, giant model. Remind me to, I'll link, I saw a cool video on, they built a model out in the desert. They kind of lit up. And so I'll put that in our content section, kind of cool, kind of scale model of but you need a lot of room. In your book, they talk about the model that they built on the Smithsonian campus in Washington, D.C., right? It extends for blocks and blocks and blocks, large blocks, to actually make that model. Okay. One interesting thing about the solar system is that it's kind of in a pancake. The planets do not orbit around in a sphere. They kind of orbit around in a pancake or pizza. It's like a giant pizza with the sun as a giant meatball in the center, and there's tinier little, meatballs that are orbiting around in that plane. All of the planets orbit the sun counterclockwise when looking down on the solar system, the North Pole of the Earth. Looking down on the Earth, looking at the North Pole, everything rotates counterclockwise. So that's an interesting fact that we need to take into account. Most of the planets also spin on their own axis counterclockwise, with 2 notable exceptions. Venus actually spins the opposite way that the rest of the planets spin, and the clockwise and the way it orbits. And Uranus actually kind of spins at a 90-degree angle. So you can think of and for thousands of years, they did kind of think of it as a mechanism with the planets all kind of spinning around like little tops as they rotate. But Uranus is more like rolling like a bowling ball around the sun. So its spin axis mathematically is 90 degrees, almost 90 degrees with respect to its orbital axis. Everything else, there's a tilt, as we learn, but not 90 degrees. Venus is actually spinning the wrong way, barely. Venus is barely rotating, actually. Okay, so I just said all that. The book goes through some things. I'm not going to spend too much time. We've already talked about most of this stuff. Right, the sun is the powerhouse of the solar system. Most of the mass, 99.8% of all of the mass, if you added up all the mass in the solar system, 99.8% of it is in the sun. And again, this is where all of the most of the energy on Earth comes from the sun. Mercury is now that Pluto is out of the picture, and we'll talk about that later. This is the smallest planet. It's barely larger than our moon. It's made of mostly metal and rock. There's no oceans. Look at the surface close up. These are where other pieces of space rock have actually hit the planet, and they leave craters. There's no water, there's no atmosphere. Because there's no atmosphere, it has crazy variations in its temperature, depending on whether you are on the sun side or the non-sun side. So if you're on the other side of Mercury that's not facing the sun, right, it's like nighttime here, it gets incredibly cold. Minus 170 degrees Celsius at night. And the difference between Celsius and Fahrenheit doesn't matter when you get to these temperatures. And on the sun side, it's very, very hot. That's the effect. An atmosphere will keep you cooler in the daytime. It'll block some of that light from the sun. It'll keep you warmer at nighttime. It's like a blanket. This is the greenhouse effect. This is a good part of the greenhouse effect. And again, Earth, right now it's a little out of skew. Earth before people got on it was just the right amount of greenhouse effect, just enough to keep us warm at night and kind of keep us cool during the day. Now that's changing because of our intervention, and we will talk about that. Actually, talk about that next week. But Mercury has no atmosphere. Venus has an out-of-control greenhouse effect. Its atmosphere is 80 times thicker than Earth's. So it's even hotter because of that greenhouse effect. I mean, this is like, right, having your grandma's comforter on top of you and having 80 of them on top of you trying to sleep at night. It's actually hotter than Mercury. And there's no day-night. It's just always hot on Mercury. It is hot enough to melt lead on the surface of Mercury. Of Venus. Not quite hot enough to melt lead on the surface of Mercury, but it is hot enough to melt lead on the surface of Venus. It is hot. The surface of Venus is hotter than the surface of Mercury. There's our lovely planet, the oasis of life. Although, as we're learning, there may be life other places, but this is the only place we know has life right now, and that has a large part to that's the only place in the solar system that has liquid water on our surface. Life as we know it, anyway, requires water. It requires a membrane that you can pass nutrients through and energy through. You need water. To make life as we know it. There are astrobiologists who think of other ways to have life, maybe silicon-based life or something like that. But This is the only object, not even planet, in the solar system that has water on its surface. But we'll learn Mars has water underneath its surface. Venus has water in its atmosphere, where it's not quite as hot. It's actually liquid water, water vapor, like raindrops, not water vapor. Water vapor is a gas, but it has liquid water in its atmosphere. There are some interesting moons of Jupiter and Saturn that have water underground. Not really underground, under ice. They have a covering of ice, and they have vast, deep, much deeper than the oceans on Earth, oceans underneath them. So it is definitely possible. I would dare say it's probable that there is life other places in the solar system, but we have not. We have some tantalizing hints of it, but we have not discovered it as of yet. One of the other unique things, and part of the reason why we have water, believe it or not, is because we have a large moon. It's also the reason why our seasons aren't so drastic. The moon kind of helps us out in many, many ways that we'll learn. But it is unusually large relative to the size of the planet. Now, the outer planets, which are much bigger, have bigger moons than ours. But the relative size between the planet and the moon that's orbiting, this is very unusual for the planets. Now, if you include Pluto, then Pluto's moon is actually almost as big as Pluto itself. Another technical reason why it got demoted to being a dwarf planet. And we're going to learn that that's really just kind of an artificial classification. Pluto is a very, very interesting and cool place. Well, it's cold, but the other meaning of cool. Mars is, Venus is like our sister planet. Mars is like our little brother planet. It's significantly smaller than the Earth and Venus, and we need to kind of account for that. In many of our early models, we would assume that Mars would be about the same size as Earth and Venus. They're really not that far apart, and they should all be about the same size. So that's one of the questions we need to answer. We'll show you all sorts of cool things. This is not the new rover. This was the latest rover that we've had on Mars. We've had dozens of them. Mars is probably, I dare say, even either we haven't sent people there, it's been more explored now than the moon has. We've sent several rovers, at least by the United States. We sent several rovers there. This thing is about the size of an SUV. The one that's on its way now is even bigger. They kind of crawl around the surface. There's geology and biology labs built right in. They can analyze rocks. They can take pictures. This thing actually shoots laser beams at rocks, and it vaporizes them, and then it can actually analyze what's inside of a rock there. And again, Venus is kind of taken over the headlines, but then recently we've discovered, even since that Venus, we've discovered more underground water, underground salty lakes under Mars. And so now the probe we just sent will not go to those lakes. We don't quite have the technology. It's like a mile underneath ice. And there's no way this little probe, even as big as it is, can drill a mile through the ice. But the new probe is actually going to go into an ancient lake bed and look for signs of life there. Not a lake underneath the surface, but a lake or maybe even a sea that was on the surface. Mars used to have oceans. Actually, we have evidence of that. Most of our models actually say that Venus used to have oceans, but because of their different atmospheres, they both lost their oceans in different ways. Mars's froze, Venus's evaporated because it got too hot. Right outside of Mars, we have the asteroid belt, which is a collection of kind of space debris, kind of, I mean, people call these failed planets. That's kind of, it's kind of rude, but they formed just like the planets did. They just did not quite get big enough to turn into a sphere. The self-gravity of an object, if it gets massive enough, will crush it into a spherical shape. All the massive objects in the universe are all either pancake shaped or they're spherical shaped. Right? If you take the solar system as a whole, it's in a pancake shape. The planets are all in spherical shape. Some galaxies are spherical. Some galaxies are disc shaped. That's the effect of gravity on large, massive objects. But if you don't quite get big enough, then gravity will not crush you into a spherical shape. And that's our definition of an asteroid or a comet. The asteroids live in between Mars and Jupiter. For most of it, there's a couple that follow. There's a lot of them that actually follow Jupiter around. There's a couple of what we call near-Earth asteroids that kind of follow the Earth around. And every now and then, one of them will hit the Earth, collide, or most likely just get burned up in our atmosphere. There's a recent one that just kind of skipped off the atmosphere. And we'll talk more about those. But then, after the asteroid belt, we much further out. We have the big daddy, the big mama of the universe is the sun. This is the big daddy of the universe. It's 300 times more massive than the Earth. The sun took most of the mass, and the solar system is basically made up of the leftovers, and Jupiter took most of the leftovers. So the Earth was kind of made over of the leftovers of the material that made the solar system. We're going to learn that none of these outer planets, as massive and as huge as they are, have a solid surface that you could walk on. They all have rings. You can't see. You can see Jupiter's rings Galileo saw Jupiter's rings with his telescope. A cheap telescope, you can see the rings of Jupiter, but they all have them. I'm sorry. You can see the rings of Saturn with a cheap telescope. You can't see the rings of Jupiter because Jupiter is reflecting so much light, it kind of drowns them out. And they're actually darker than the rings of Saturn, so they're not as easy to see. But all of the outer planets have ring systems. They all have many, many, many moons, dozens of moons. So many moons that we just recently, within the last year, discovered dozens of moons of Jupiter and Saturn that we didn't know of before. So they all have lots and lots of moons. And as I said, some of those may be a good place to look for life. There's a picture of Saturn. It's got spectacular rings, and it's got another planet that may have a different kind of life on it. Titan kind of looks like Earth from outer space. And there's liquid on the surface of Titan. It's the only other object in the solar system that has liquid on its surface. It has seas, but they're not made out of water. They're made out of methane and ethane and ethanol, basically natural gas. It's incredibly cold, but at those temperatures, water is frozen. The water on Titan is in the form of mountains that are made out of ice. There's some sand on the planet. And these oceans here, they're not liquid water, they're liquid methane. They're like lighter fluid. So if there's life on this planet, it's going to be that, maybe based on not water, but based on methane or ammonia or something like that. And we'll talk about that. So another place to look for life, only it'd be a different kind of life than what we have on Earth. Those rings, they look like giant, plexiglass, features of Saturn aren't very, they're not solid at all. They're actually made up of tiny, tiny little hunks of rock and ice. The reason why they're so visible is because, as we learn, ice has the largest albedo. It reflects light better than anything else. That's why we can see Saturn's rings from Earth with a tiny telescope, because not all of them are made out of ice, but a large number of the ring material is made out of ice. Then we go on to the ice giants, Uranus and Neptune. They're still much larger than Earth, but they're smaller than Jupiter and Saturn. And they're made out of these compounds, water, methane, and ammonia, and mostly in the form of ice, but not like ice, not like a glacier type of ice, like snow kind of ice. It's more of a powder. Again, there's no solid surface on Uranus or Neptune. Even their very, very cores, maybe there is some solid rock down there, but it's probably liquefied. Neptune is similar to Uranus, except it's tilted better. Here's a kind of all of these planets are kind of pictured with along their orbit in this way. So you can see. They all have a little bit of a tilt, but Uranus has a huge tilt. It's moving in this direction, and it's spinning in the direction of its rings up here. One of the other interesting things about Uranus and Neptune is that Neptune is more massive than Uranus, and our early theories of the solar system said that should be different. In general, when you're in the outer part of the solar system, the closer you are to the sun, the bigger you should have been able to get. That's why Jupiter is much bigger than Saturn, and Saturn is much bigger than these other two, but these other two don't quite, we would expect that Neptune would be much less massive than Uranus, but actually Neptune is more massive than Uranus. And then concluding our brief tour of the solar system, we have where the comets live. The comets are, again, they're like asteroids. At one time, we thought they had more ice content, and that would make sense. They're further away from the sun, so you expect them to have more ice. But it turns out comets and asteroids are more alike than they are different. So the only real difference between a comet and an asteroid is where it normally lives, where it spends most of its life. And that is in the Kuiper Belt, which is in the same pancake shape as the rest of the solar system, kind of like a donut shape out here. But the Kuiper Belt, most of the objects they orbit counterclockwise. But they spend most of their time out here. But they do get closer to the sun sometimes, and when they do, that's the comets that we can actually see in our night sky. You can't see this stuff, but right, that comet Neowise, I don't know if any of you saw it. When the comet, it spends most of its life either in the Kuiper Belt or the Oort cloud, but it's still in orbit around the sun, so it'll get closer to the sun. Remember, it moves a lot faster when it's closer to the sun. It moves really slow out here. Those are how we can see them. And again, every now and then, one of these will collide with with one of the planets. But then we have, we kind of break that pancake shape, or that pizza shape, and we have another place where the comets live, which is called the Oort cloud. And this is a sphere. It surrounds the solar system in 3 dimensions. So it's kind of like a pizza with a ball around it. And that ball is where the comets live. And again, they have more random orbits. Not kind of, we kind of lost the counterclockwise thing. And again, they spend most of their life here, but they still come down and they visit Earth and the sun. They're really visiting the sun, but sometimes Earth, sometimes Earth really gets in the way. And the dinosaurs did not like that the last time a big one that happened, and they collide with the Earth. But usually it just gives us a nice, a cool little show at night. We can see the tail of the comet. It's not really orbiting the Earth; it's orbiting the sun, and we're just in the way. Okay. Let's talk about Pluto. Pluto is even further out. It's much smaller than the other planets, and it's rocky and icy. It has more ice on its surface than any of the other planets. As you would imagine, it's way, way far away. And then here's a picture of its moon. Its moon is Charon. It's similar in size to Pluto. But again, there's other dwarf planets. They're all smaller than the moon. Pluto, Eris, Haumea, Makemake, Ceres, several others discovered since this slide. This is one of the reasons why Pluto got demoted, is we would have to add these other objects in our planets. And I guess they didn't think grade schoolers could memorize that many planets. I don't know. We actually have recently discovered another dwarf planet, which has been called the Goblin. I say recently, is 2015. That's when we first got hint of it. It takes years and years for us to really verify that these objects are what they are. This is how difficult it is to observe these Kuiper Belt objects. This is with now these are stars. These are easier to see than planets that far away because they have their own energy source. What we're seeing here from Goblin here is the light reflecting off the sun, and we have to look at it for months and months at a time, and we can just see that it's barely moving. Remember, the stars aren't going to move on the course of a couple of months, but the planets actually do. Hold on, I have a chat question here. Let's see what we have. Okay, there we go. Good question. Why is Haumea the only one that's non-spherical? Because Haumea is actually still getting crunched. If we look at Haumea in another 1,000,000 years, it will be spherical. So we can kind of see it's massive enough, and we can it's actually still forming into that sphere. But good question. It's an egg shape, so it's kind of in between an asteroid and a dwarf planet. One of the interesting things about Goblin and Sedna and many other of these massive objects in the outer part of the Kuiper Belt is that we keep finding them on one side of the solar system. And there's no reason why they should be on one side of the solar system. All right, they should be, there's enough of them that on average they should be on both sides, on every side of the solar system. So that all of their orbits are kind of skewed to one direction, and we think that is because there is another massive object out here. which has a mass about 10 times the mass of the Earth, that lives out here. And that is the hypothesis for that is Planet X or Planet 9. And so let's watch this. Let's watch this video about Planet 9.
Numerous features of the Kuiper Belt, a field of icy debris beyond the orbit of Neptune, can be understood if the solar system possesses an additional 9th planet that resides well beyond the orbits of the known planets.
When we look at the outer solar system, we realize that while most of the very distant objects, these objects beyond Neptune, beyond Pluto, most of these objects, they all go around the sun and they're all sort of pointing off in all different directions. But the most distant objects all swing out in one direction in a very strange way that shouldn't happen. And we realize that the only way we could get them to all swing in one direction is if there is a massive planet also very distant in the solar system, keeping them in place while they all go around the sun. And we started looking at this and thinking, this must be either a coincidence or it's caused by something else. It can't be caused by a planet because that's crazy. There are no planets out there. I went from trying very hard to be skeptical that what we were talking about was true to suddenly thinking, oh, this actually might even be true.
So the object itself likely is more massive than the Earth, probably a little bit less massive than Neptune. It sits right in between that terrestrial to giant icy planet range. Its orbit, unlike the orbits of the known planets, is not nearly circular and planar. Instead, it is exceptionally wide, 20 times bigger than the orbit of Neptune. The orbital period of the Earth is, of course, 1 year. The orbital period of Jupiter, the big player in our solar system, is about 10 years. The orbital period of this putative 9th planet is 20,000 years.
We have nothing like it in the solar system, so it's new for us. It is, however, the most common mass of planets that have been found around all of the other stars. People have always looked at all these other planets in this strange mass range and said, wow, I wonder what these are. I don't know what these are because we don't have anything like it in the solar system. Looks like maybe we do. There are many telescopes on the Earth that actually have a chance of being able to find it. And I think that many people will be inspired to use their telescopes. I'm really hoping that as we announce this, people start a worldwide search to go find this 9th planet.
History shows us that it's a bad idea to consistently say we have now reached the end of the solar system and there's nothing beyond what we already know.
And all those people who are mad that Pluto is no longer a planet can be thrilled to know that there's a real planet out there still to be found.
So that video is probably about 5 years old by now. And yes, we have been looking for it. And no, we haven't found it. Now, of course, you saw how hard it is to find Goblin. Actually, we were looking for Planet 9 or Planet X and that's how we found these other dwarf planets. There's actually been a new hypothesis for another. I mean, it's pretty clear there is something out there, but it doesn't necessarily have to be a planet. There's a new hypothesis that there's actually a black hole out there. Don't be afraid of black holes. It would make no difference whether it was a planet or a black hole out there unless you got right up onto it. And it's very, very far away. This black hole, a 10 solar mass black hole, a 10 Earth mass black hole, is about the size of a grapefruit. It's a tiny, tiny black hole. It's called a primordial black hole. We'll learn there's different kinds of black holes. There's supermassive black holes we've already talked about. There's stellar mass black holes. When a star dies, it produces a black hole. Some of them do. The sun won't, but more massive stars, when they die, produce black holes. And primordial black holes, nobody's ever discovered one yet. They're theoretically were produced at the beginning of the universe. So there might be a black hole out there that's causing that. That remains to be seen. Okay, so that's our tour of the solar system. and we want to make a model of how the solar system formed. Another piece of crucial information would be how old is the solar system? Is the solar system as old as the Big Bang? Is the solar system as old as the Milky Way galaxy? Is the sun older than the planets? Or the planets all different ages? Maybe the big ones are older than the little ones, and the little ones are going to turn into the big ones if we give them enough time. So we need to understand how old the objects in the solar system are. So let's start with the sun. The sun is a very different object than a planet. It's different processes of physics going on. That energy generation actually allows us its temperature, its size, and how much energy it's putting out by studying literally millions, hundreds of millions of other stars. Allows us to put an age on the sun. And there's about, we'll learn, there's about 3 different ways we can tell the age of the sun, and they all give us an answer of 4.6 billion years old. Okay, so the sun is that old. We can actually determine the age of the Earth by studying the rocks, studying the radioactive decay of the rocks on the Earth. And you'll do a little homework tutorial about that, and I'll talk about it briefly. The radioactive elements inside of rocks are kind of like hourglasses. And as the element decays, for instance, uranium will eventually decay into lead. If you take the ratio of uranium to lead, you can tell how old a rock is. So we can determine the age of the Earth, sort of. We're going to learn next week that the surface of the Earth is constantly recycling itself by erosion and volcanic eruptions, and most of the surface of the Earth is only a couple of billion years old. But there are some special places. The first continents on Earth are about 4.3 billion years old. As you saw in our discussion video, we brought back rocks from the moon, and the moon's surface has not changed. There's no erosion. There's no volcanic activity anymore. The surface of the moon hasn't changed for 4+ billion years. And the rocks that the astronauts brought back are 4.5 billion years old. The pieces of space rock that we don't go get, but actually Earth gets for us, those asteroids or any space debris that falls, gets caught in Earth's gravity well. Most of them burn up in our atmosphere. Most of them burn and then explode. But sometimes, and often, the debris hits the Earth. It's usually just in tiny little pieces called meteorites that we can collect, and we can study them. And they are the asteroids that hit the Earth are 4.5 billion years old. Here's that radioactivity. It's the actually nucleus of the atom, not the electrons, but the protons and the neutrons. When you have very, very heavy nuclei that have lots of protons in them, they're unstable and they decay. But even carbon is a little bit unstable. The heavier isotopes will decay. You've probably heard of carbon dating if you've ever taken a biology or an archaeology class. It allows us to tell how old a bone is. But carbon dating only works for things that were alive. We can't use carbon dating to tell the age of a rock, but we can use a similar process called radiometric dating. Again, we could use, instead of taking the ratios of carbon, we can take the ratio of uranium to what it decays into, lead. And so we have a rock, and specifically the rocks that we use are called zircons. They're tiny little crystals that are really hard to destroy. And they have a tiny little bit of uranium in them, and they have no lead in them when they were born. But over millions of years, over billions of years, some of that uranium gets turned into lead. And we know, you don't need to know the details of this, but we know the process of uranium turning into lead, and we know how long that takes on average in the laboratory. And so we can, by taking the ratio of the daughter to the parent atoms, we can tell how old a rock is. For instance, we start with, let's say the blue here is uranium, and then the daughter is lead. We actually talk about what's called the half-life. The half-life is how long on average it would take for half of that material to have turned into, to decayed into its daughter. So after one half-life, we'd have a 50-50 ratio. After two half-lives, it would be 3 to 1, and so on, until we would get, you can kind of see the parent gets smaller and smaller. It gets so small that, after 5 or so half-lives, we can't even measure it anymore. So you have to find different elements to determine the different ages. But to get the oldest rocks on Earth, we actually do use uranium. There's different kinds of uranium, but it has a half-life of 4.5 billion years. So it's good for us to determine the age of the rocks on the Earth. So again, here's some examples. Moon rocks, 4.5 billion years old. The oldest piece of space rock that we have ever measured was found in the Sahara Desert. This is the name of that meteorite, but it's this little clump of material here is 4.57 billion years old. Keep this picture in your mind. This is called a carbonaceous crondite meteorite. That's not the important thing, but this is the poster child for the nebular theory. Remember, the nebular theory says we all were formed by gravitational collapse of this dust and gas cloud. And the dust cloud gets bigger, and it forms these little rocks, and then it smashes into another rock. And over millions and millions of years, it forms these big structures. You can actually see this. This particular type of meteorite has not gotten hot enough to melt. It hasn't changed since it was made. So this is these meteorites are some of the best places for us to test our models of how the solar system formed. Not just their age, but look, the composition. You can see how this was made up of tinier and tinier objects. And really, this is what the Earth looked like. In fact, the Earth started, as a tiny little dust bunny. And not necessarily by gravity, but by static electricity, started to be attracted to other little pieces of dust, and got bigger and bigger and bigger and bigger. And over millions of years, it turned into the Earth. But you can kind of see that process, not in action, but the result of that process in these we call them. You can call them carbonaceous crondite meteorites. Trust me, I'm not going to test you on that, but we kind of talk about the ancient meteorites that haven't changed. Kind of a cool thing is we actually, we find pieces of Mars on the surface of Earth. So how does that happen? Well, you saw those giant craters, especially when I showed you the picture of Mercury. Those, and it may be, you'll have a better sense of the size of them when we actually study Mercury in more detail. But they're some of those things they're like tall mountains in the center, and they're deeper than the Grand Canyon. Tremendous impact that blows off pieces of the planet. Most of them come raining down. And come back down to the surface of the planet, but sometimes they get shot out into space. So it's like a giant bullet hitting a grapefruit, and the grapefruit, I mean, the whole planet doesn't explode, but pieces of it explode, and some of it gets sent off into space, and some of it, we are very close to Mars sometimes, some of that debris gets caught in Earth's atmosphere and comes down to hit the Earth. So we actually have meteorites that are from Mars. How do we know they're from Mars? Because we can analyze the chemistry of them, and we have our rovers on Mars that analyze the chemistry of the rocks. Every planet's rocks are a little bit different, or a lot of bit different. Actually, they're certainly different enough for us to tell where a piece of rock came from. So we know that these meteorites came from Mars. This one was found in Antarctica. It's easier to find meteorites when there's no other rocks around. So a lot of them are found in Antarctica or the North Pole, and in the desert where you don't have. When you find any rock, it's pretty clear that it's going to be from a meteorite. This particular meteorite is actually very famous because some scientists think that there are fossilized microbes in it. Not just how old it is, but it's kind of interesting. You can kind of see these little cells lined up, but turns out that you can make those features with just normal geology too. So it's some controversial evidence of life on Mars. And then finally, here is the oldest piece of crust of the Earth that we know of. I mean, it's kind of tied. There's about 3 different places on Earth. This one is in Hudson Bay in northern Canada, near the Arctic Circle. That rock right there is 4.3 billion years old. There's another place in South Africa. There's a place in New Zealand where we can find some of the original crust of the Earth. Remember, even the crust of the Earth has changed. You've heard of Pangea. We have continental drift. We scientifically call that plate tectonics. We've had supercontinents, and we've had the continents breaking apart. The continents actually are right now still moving, and they are slowly forming another supercontinent. And so our crust is constantly being recycled, but there is some of the earliest crust left. 4.3, don't take that as being that the Earth is 2.2 billion years younger than the rest of the solar system, because we know it took time for the Earth to actually solidify. It was a giant ball of lava for its first 0.2 billion years of existence. And actually, we'll talk about how it actually was solidifying, and then it got re-liquefied again. Let's see. Yeah, let's spend another couple minutes and talk about the nebular theory. So the nebular theory is that the solar system, and not just the solar system, all stars and now all planets are formed from these gigantic clouds and dust and gas. And notice this is 100,000 AU right here. So this thing is not, this cloud of gas, dust and gas is not going to form one star system. It's going to form dozens of star systems, hundreds of star systems. If you haven't yet, look at the picture on our content section of what's called a stellar nursery, a giant cloud of gas where we see baby stars being formed, and we see infant stars that have just turned on. And that's what we mean by the nebular theory. A nebula is a giant collection of dust and gas. And we're part of this. This is that part of the cosmic recycling process that we talked about in week 1. Stars and planets are formed from this cloud and dust and gas. The stars go on and live. They don't live forever. When they die, they either gently lose their atmosphere, which makes another cloud of dust and gas, or they explode, which actually produces more heavy elements. And stars and planets are made out of that, more enriched with heavy elements, gas and dust. As I said, the sun, the Earth is a third generation of this recycling process that goes on there. The first planets in the universe were not rocky planets. There wasn't any of that material. It was all just hydrogen and helium. Our best piece of evidence, because we do not live in a nebula anymore, right? We are, we're kind of in the sticks in the Milky Way. We are not surrounded by a tremendous amount of dust and gas and other stars. So the best evidence for the nebular theory is not from the solar system. It turns out that just like people, you don't always stay where you were born. You move out of your city. We left our cluster of stars, but we can still see clusters of stars, and more importantly, for the nebular theory, we can actually see baby stars being born in these giant clouds of dust and gas, and we do not see baby stars being born out of the middle of nowhere. And so this is our primary evidence for the nebular theory, although we'll learn it explains a lot about the solar system. It really comes from studying other stars, other star systems. And these are, again, these are in infrared. You can see these are called protostars in the center, and then kind of the dust and gas is swirling around, and that's where the planets are going to be made. In here. Again, you can see this with your own eyes. You won't be able to see this unless you can see in infrared. But you can see kind of the fuzziness in the Orion Nebula, the Orion constellation. You can kind of see this little kind of purple or red patch in there, and that's what you're looking at. You're looking at what's called a stellar nursery, where baby stars are being born. I'm going the wrong way. Here's another famous one called the Pillars of Creation. These are all taken by the Hubble Space Telescope. These things are light years across, and then hidden in here, you can see another. You can see stars being born in these giant clouds of dust and gas, and then some more. This one is some further evidence. Remember that the hotter stars shine blue, and we're going to learn, and we learn by studying millions and millions of stars, that the blue stars don't live very long. They're more massive, they're hotter, and our laws of how nuclear reactions work, we can study those in the laboratory. Predict that they should not live very long, and then we can go out and measure the little ages of blue stars, and we never find an old blue star. So when you see a blue star, you are looking at a baby star. And so again, we see these blue stars in these stellar nurseries. They're older than but we can actually see them in visible light. So whenever you see a blue star from now on, you're going to know that's a region. When you see a bunch of them together, you know that's a region of star formation, whether it's a picture of a nebula or a galaxy. We can tell where the stars are being formed by looking for the blue stars. So that begs the question, we left our town, we left our star cluster, where did we come from? Where was the sun born? Like, we're out in the middle of nowhere. If we look at, you might think, well, maybe we are from a small town. We're not from one of these big star cities. Maybe we were born in a small town. So let's look at the stars around us. Maybe you can make stars out in the middle of nowhere, like we have towns out in the middle of nowhere. And so we measure the chemical composition of all the stars around us, and none of them match ours. When we look at the chemical composition in these clusters, they're all they have the same chemistry, the same amount of chemicals, different. I mean, nothing is different on the periodic table. It's just how much of each element you have. When I say the chemistry is different, the abundance of the elements is different. We have to kind of, and while we are beginning to map all of the motions of the stars in the Milky Way, we've been moving for a good long time, almost 5 billion years. We don't have a map that, tracing our paths back that far yet. So what we do is we kind of randomly search for stars in the Milky Way that have a similar chemistry to the sun. And when we do that, it's not overwhelming evidence, but it's kind of pointing us to this. So if you had to, I would say, this is our best guess, is how I would say this. Is that the sun was born in the M67 star cluster, which was named the King Cobra cluster. I don't know why, but doesn't look like a king cobra to me. But that's cool to have on your birth certificate that you were born in the King Cobra cluster. It was actually named that before we knew that Earth may have came from there. So that's a cool little thing. I think we will stop right there. So now we know, we have a good idea where we came from, and the basic structure of the solar system, all the things that we need to, our theory needs to explain. And we'll spend next Wednesday talking about how all of this stuff was formed, now that we know the ages and the structure of the solar system. Okay. Any questions or comments on this? Okay. One heads up to you. Believe it or not, we have to start thinking about the midterm. It's in 3 weeks. Part of that thinking is we all need to take it together, not exactly at the same time, but within a day and a half of each other. That's our new rule. It's not going to be proctored yet. We don't have any remote proctoring, you're kind of going to be on your on the honor system here. Technically, it's not an open book exam, but obviously I'm not going to monitor you. I'm not going to be able to tell whether you're looking at your book or not. We will be able to monitor your mouse clicks, though. So if you plan on using Dr. Google to answer the questions, you'll get caught doing that, at least if you do it on your same computer that you're taking the test on. It's going to be completely randomized, and honestly, you're not going to have enough time to look up anything on Google anyway. So now's the time to to think about studying for it. It will cover this week, and it will cover next week. And so, you know, the way to study for it is obviously to do your homework. I'll open back up the discussions so you can go and look at them and see what the answers were to them, the quizzes, the learning objectives in our content section. But what I also find that helps us study for that is if I actually help as well. If we all together make a study guide, an online kind of study wiki. And so I'm going to open that up by tomorrow morning. And it'll have a list of all the topics that will be on the midterm. And I want you to each choose one, and I think it's only going to have to be one. I'm pretty sure it's only going to have to be one. We have enough people. So you're each going to choose one subject to pick it, and I want you to summarize it for the rest of the class. So we'll have kind of a study guide that we build together for there. You'll see my example of it. I'll do relativity, and you'll see my example of it, and just kind of follow that lead. And you'll see the instructions on that. Again, first off, just pick your subject. First come, first serve. You can't, you know, just like our telescopes, you need to pick pick a different subject than somebody else. It won't be, I mean, I just get it picked and then kind of think about what you want to do and start thinking about studying for the midterm. You'll see more details when when I announce that assignment gets open. All right. And then the other thing about the midterm is if you have, it'll be during the week. I think right now it's scheduled for Monday night, and then that means you would have until Wednesday morning to do it. So if that does not work for you, if you need to let me know now, and we'll decide as a class when to take the midterm together. So if you have some constraints for that week, let me know what it is. That week is actually in the syllabus, so you can look and see what it says. It's the 20th, but we have some wiggle room on there. We can make it a little bit later in the week if you all want. All right. I don't want to make it earlier. I want you to be able to ask questions that Monday before the midterm. So it will not start before Monday at let's say 8 o'clock. But we could push it back a day or two after that if somebody has a reason for that. All right. Okay. All right. I don't see any questions, so you'll all be good. Keep up the good work. Remember to choose your midterm topic as soon as possible. And before class on Wednesday, make sure that you have replied to at least 2 of your classmates' discussion posts. I enjoyed reading your science fiction. That's cool. And so keep that discussion going, and make sure you get it done before the end of class, or before the beginning of class on Wednesday. Be good, be safe, and I'll see you on Wednesday.